Hey class, Professor Larrick here with a brief introduction to wind. Let's cover the basic principles behind how the wind is created, the physical scales of motion, the numerical scales that we use to quantify wind speed and direction, and the instrumentation used to measure these quantities. To understand why the wind blows, check out this short tutorial from PBS. Hopefully some of the concepts sound familiar from previous videos.
The word wind can mean many things. It can be peaceful, violent, powerful, exciting, bitingly cold, or searingly hot. Wind is everywhere all the time, but where exactly does it come from? I mean, it's only air, which we've talked about a little before, but there are no fans or turbines or giant people in the sky blowing the air around, so where does the wind come from? Even when you don't feel the wind, the air is never totally still. If you zoomed way in, you'd see air molecules bouncing around, colliding with each other and everything around them. Now, all that bumping and bashing creates a force. It's the force of all those bouncing air molecules over a given area of Earth that results in pressure. See, air has mass, and gravity drives that air down towards the ground. That's why there's more air pressure down here than there is, say, on top of Mount Everest. The average atmospheric pressure on Earth is about 1 bar, or 100,000 pascals. But luckily, that pressure isn't pushing straight down. The force goes out in all directions, so we aren't squished into pancakes. Wind is what happens when air moves from high pressure to low. Anyone who's ever watched the weather knows that air pressure isn't the same everywhere, and that's because of temperature. Air near the equator is heated by the energy of the sun, so it becomes less dense and it rises. Near the poles, there's not as much heating by the sun, and that cold, dense air sinks down toward the Earth. Right along the equator, that creates this area with almost no wind called the doldrums. But wind doesn't come straight from the north or south. The Earth is turning, and because the atmosphere isn't attached to Earth, that causes the wind to curl and rotate. That's known as the Coriolis effect. If you want to experience that, just try to play catch on a merry-go-round. Pressure and temperature combine with a rotating Earth tilted on its axis and covered in sun-absorbing land masses. The winds of the Earth begin to swirl like a Van Gogh painting. So begins the swirling cycle of heating, cooling, and rotation that drives everything from gentle breezes to destructive hurricanes. Sometimes a little science can just blow you away.
I know what you're thinking. Professor Larrick is so much cooler than that guy. Well, you're right, and thank you. Now, the global wind pattern continually circulates around the Earth, blowing air from regions of higher pressure to regions of lower pressure, and this is called the general circulation, seen here in a numerical simulation by a group from the National Center for Atmospheric Research, located down in Boulder. Now, we'll learn all about these global winds in future lessons. For now, just be aware of its existence and the fact that smaller scale circulations actually develop within it. Examples include mid-latitude cyclones, which are on the order of 3,000 kilometers wide. These systems can bring about a plethora of dangerous weather conditions across the country and the rest of the world. Hurricanes are smaller, on the order of 300 kilometers wide, but we all know that they can yield devastating weather conditions across the eastern US as well as other regions across the world. Embedded within mid-latitude cyclones and hurricanes, we have individual thunderstorms, and these are another order of magnitude smaller, on average about 30 kilometers in diameter. And then the cloud tops can actually be even larger, as you can see individual storms rolling across the Texas Panhandle. Individual components of thunderstorms are even smaller. The animation in the lower right-hand portion of your screen shows a severe thunderstorm that we call a supercell. Notice that there's evidence of rotation throughout the entire storm. The lowest portion of this rotating cloud is called the low-level mesocyclone. This is only on the order of 1 to 2 kilometers wide, but within that, we can spawn tornadoes, which are even smaller. On average, tornadoes are only about half a kilometer wide, or 500 meters, but as you probably know from documentaries, movies, maybe previous science classes, tornadoes can vary in size, depending on the storm that creates them and their overall intensity. Now, we'll be learning all about tornadoes and their impacts later in the semester. But it doesn't matter whether we want to measure winds in a powerful Midwest blizzard or a tornado-producing thunderstorm down in Oklahoma. Meteorologists must consider both wind speed and wind direction in order to quantify what the winds are doing. Wind speed is typically recorded in knots although you may be more familiar with the American units of miles per hour, and then scientists tend to make calculations in meters per second. Wind direction, on the other hand, is reported in degrees, and the standard convention in meteorology is to record the direction the winds are blowing from. We can visualize this using the compass in the lower right-hand portion of your screen. By definition, winds blowing north to south or from the north is defined as 0 degrees, and then that direction increases as we move clockwise around the compass. For example, let's say that we have wind blowing from west to east at a location, visualized by the thick arrow that just popped up on the compass. Well, from west to east, as you can see by the compass dial, is defined by the 270-degree tick, which means if winds are blowing from the west, that is a 270-degree wind. Now, we'll stick to degrees when it comes to wind direction, but when it comes to wind speed, we might have to convert between scales once in a while. So let's make sure we understand those numbers. 1 knot is equal to 1.15 miles per hour, which is also equal to 0.51 meters per second. Let's say that the winds are blowing at 100 miles per hour, and we need to convert this value to knots. Well, we know that for 1 knot, there's 1.15 miles per hour. So we multiply the value by that ratio so that the miles per hour cancels out, and we'll just be left with knots in the numerator. And when we do that, 100 divided by 1.15, we'll get about 87 knots. On your own, see if you can convert this value to meters per second. If you do it correctly, you should get a value of around 44 meters per second. 2 weather instruments are required to measure winds, one for speed and one for direction. Direction is measured by a simple wind vane, comprised of a compass and an arrow with a rear fin and weighted tip that's guided by the wind. The direction is ultimately measured by the compass direction associated with the tail of the wind vane, either matched up manually or by an analog to digital signal. The speed of the wind is measured with a device called an anemometer, the most basic of which is a cup anemometer. Composed of 3 to 4 cups about a rotating axis, the wind blows air into the concave portion of a cup, and that forces the device to spin. And the rotation rate of the device is a function of the wind speed. So if we know the overall diameter of the instrument and the revolutions per minute, the wind speed can be calculated using a relatively straightforward equation. Now, of course, the ultimate goal is to take these concepts of wind speed and direction and use them to learn about all of the powerful circulations that can result in devastating and sometimes deadly weather disasters across the globe, including hurricanes and tornadoes. But that's all for now. Until next time.